Hello, welcome back. Now we're going to be doing the last bit of topic 5, which is entropy and spontaneity. A spontaneous process, let's first define. So, the first law of thermodynamics allows for insight into energy, but it doesn't really give us any insight as to if something will happen. And that's what spontaneity is a measure of. So a spontaneity is defined as how much outside intervention is needed for a process to occur. So, for example, a ball will roll down a hill but not up a hill. A gas will expand to fill one end of the container but not pile up in one corner. Most chemical reactions need a small input of energy. This involves the activation energy, which is a kinetic consideration. However, thermodynamics generally only deals with will this process happen or not. It doesn't deal with how fast it would happen. But it gives us insight as to something if it will happen, which is really important. Um, Now, for example, it gives us insight into the spontaneity of reactions. So, for example, freezing of water is exothermic, so which means naturally, because of that, I told you earlier that nature wants to be in a low energy state. So, shouldn't it always happen? Well, the reason why water doesn't always frozen is because it's not spontaneous below it's not spontaneous above 0 degrees centigrade. So that's something you have to consider. The two other factors that you want to, the other factor you want to consider is the change in entropy to the reaction or system. And bringing those concepts together, you can get something called the change in Gibbs free energy, or the Gibbs free energy, which is an indicator of spontaneity, which is the main indicator of spontaneity. You should be familiar with this course. Uh, Entropy, it's hard to define at this level, but at your level, it would be sufficient to say it is a measure of disorder or molecular randomness within a system. So, um, delta S is the difference in entropy or disorder between the final and initial states. So, entropy entropy is a thermodynamic function related to the probability of certain microstates, macrostates, or microstates occurring. I mean, no, each microstate is equally likely, but certain configurations, certain types of microstates are more probable than others. So, to I suppose for those of you that are that would have this sort of mathematical background, if you consider a microstate as a permutation, each permutation is equally likely. However, if you don't care about order, the arrangement of things, so you use the choose function rather than the pick function, you get a lot more choice. Some configurations are much more likely just because some combinations are just more likely since they can happen different ways. So, say for example, if we look at this very simplified example here, ABCD versus empty is 0, well, that's 6.25%. Or if we wanted one part, so if we wanted, say we had a system of 4 particles, um, if we wanted them all on one side, there's only one way that can happen. And similarly, if we only wanted one on the other side, there's only one way that can happen. Well, for if we wanted only one particle on this box or the other box, it really doesn't matter which one we pick since it's the same calculation. We would do 3 choose 1 times, no, 4 choose 3 times, uh, yeah, 4 choose 3 times 4 choose 1, which you can either have A, B, C, and D, A, C, D, and B, A, B, D, and C, and B, C, D, and A, which those are 4 of the possible 16 microstates. Since we have 4 particles and they can go anywhere, 4 squared is 16. And then lastly, the reason why an evenly spread system is most likely, we could have A, B, C, D. If we wanted 2 and 2, we could have A, B, C, D, A, C, B, D, A, D, B, C, C, D, A, B, B, D, A, C, and B, C, A, D. Or 4 choose 2 times 4 choose 2. And that is 4 choose 2 plus 4 choose 2, whatever it is. Whatever the mathematics works out to, we can clearly see that this microstate is just more likely to happen as a result. So this combination of microstates, since the majority of the microstates lead to this combination here, this configuration is just more likely. And as a result of that, that's sort of what it wants. And as a result of that, since that's the most probable outcome, that has the highest amount of entropy. So that's sort of what we. This gives you a sense for of what entropy really is. Now, this is a very simplified example, and the calculations get much more complex the more particles you have. So if you have a mole of particles, 6.022 times 10 to the 23 particles, you would do that math over and over and over again. So that's the idea of, well, in this case, that would be the idea of positional entropy. There's also state entropy and all that stuff. If you take a thermodynamics or a statistical mechanics course in university, you'll really get a feel for this stuff. But for now, this is good enough. The expansion of gas has high entropy because it increases the number of possible positions for the gas particles. If you are allowed to take up more space, there are more positions that each particle can occupy, and therefore that maximizes entropy. Gases have a lot more entropy than liquid and solid, again, because they can occupy more microstates. They can just fill the space more, and as a result of accessing more space, there are more configurations of particles that can be accessed. Increased motion of particles, again, a higher temperature, also increases the entropy because they can go further and occupy more microstates. Lastly, more complicated molecules just have inherently more entropy than simple molecules. So big molecules that can rotate and have rotational freedom, that has more entropy than just, say, a simple molecule of CO2. You're going to be asked to predict the sign of delta S for some reactions. You could just use the rules above that I just discussed to sort of do that. So for example, predict the sign here on A, which, since we know going from a gas to a liquid, since a liquid has less mobility than a gas, they can occupy less microstates and therefore should have a decrease in entropy. So there should be less disorder. And you can do the other ones for yourself. I personally don't care. But that's sort of the idea behind it. Let me just make sure this is recording. Yeah. Now, let's go over the third law and the second law. So, but 1 second, I need to get a quick drink of water. Alright, whatever. Oh, back. Shit, I have to do that form at some point. Regardless. Alright, now that drink of water is done, I just had to check my email there for a second. Although it makes no sense to introduce the third law before the second law before the third law is more prominent to what we're talking about, which the third law states that a perfect crystal at absolute zero has no entropy. Now, what does that mean? Unlike delta H, which we couldn't really measure entropy, we can measure entropy because it's relative to something. And you'll be given a table of values, but the delta S is just the entropy of the products times the entropy minus the entropy of the reactants. Pretty simple. And a similar sort of format for the Gibbs free energy. They all follow the same formula. And then the second law states that the entropy of the universe is always increasing, or at least that's one statement of it. Entropy always increases, and that's sort of actually why you can only go forwards in time and not backwards, because since entropy must be greater as time goes forward, you can only go forward in time and increase in entropy. You can't decrease in entropy because going back in time is not possible yet, or ever, I don't think. But that's a nice little aside. Reactions are spontaneous if the reaction increases the total entropy in the universe. And we can take the delta S of the universe is the delta S of the system plus the delta S of the surroundings, which we can calculate with this thing. You don't have to remember this, but delta S in surroundings and delta H will always have opposite signs by definition. So a reaction is exothermic, the delta H is less than zero. There's less disorder in this. There's less disorder. The surroundings of the system are more disordered, and the opposite is true. To sort of relate these two, we can create a new function called the Gibbs free energy, which is the enthalpy minus the T delta S, which basically the free energy is more or less the capacity to do useful work. So, i.e., how much energy is really available to you when you have the system undergo a chemical change. And then the change in Gibbs free energy is given by this reaction, delta H minus T delta S. And if the Gibbs free energy is less than zero, the reaction is spontaneous, and the inverse is true. Here, you don't have to memorize this table. You can just do math Like, if you put a negative here, negative times a negative is a positive, and that's positive. Well, there you go. The Gibbs free energy is positive. Um, if this was negative and this was positive, then you would always write it depends, or is t dependent. Is what you would normally say. But that's sort of the idea there. You want to come across. I'm not going to go over these. You know how to plug and chug numbers into a formula. I don't think it would be fair to you for me to go over sample calculations. Um, and then the Gibbs free energy formation, we could just do this. It's like the delta HF formation. I don't think it's worth going over these. If you do want me to go over them in a separate video, of course, please do leave a comment. But if you want to calculate, but I suppose there's one last note I want to give regarding state changes. Using melting as a state point as an example. The Gibbs free energy when you do state changes, or when we discuss later, the Gibbs free energy at equilibrium, or the change in Gibbs free energy at equilibrium, is actually zero. Which, that's actually a topic for the equilibrium section, not this section. And this concept of spontaneity and Gibbs free energy and all that stuff, it'll come back to haunt you. So get familiar with it now and get used to it. With that said, thank you for watching. Don't forget to like and subscribe.